Welcome to the deep dive. Today we're tackling prompt engineering. You fire off prompts to AI all the time, right?
Yeah, constantly.
But turning those casual chats into really targeted requests that get you seriously insightful outputs, well, that's the skill we're digging into.
Exactly. Think about asking a chef for food versus asking for a specific dish, right? Cooked a certain way with particular ingredients.
Good analogy.
Prompt engineering is basically giving the large language model those specific instructions to get the results you actually need.
And that's precisely what we're going to explore for you.
Yeah.
You sent us a fantastic detailed paper on prompt engineering. And our mission, really, is to extract the core insights, the stuff that makes you think, aha.
Yeah, the key takeaways.
So you can grasp it quickly and thoroughly without getting bogged down, whether you're gearing up for a crucial meeting, trying to get a handle on a new subject, or just, following your curiosity. This deep dive is for you. We aim to demystify this whole area and give you some practical techniques you can immediately understand and maybe even put to use. Okay, let's get started.
So let's maybe lay the groundwork first. Understanding how these large language models, these LLMs, actually operate.
Good idea.
Imagine them as incredibly advanced autocomplete systems. I mean, seriously advanced.
Okay.
They've been trained on just vast amounts of text. And when you give them a prompt, they're essentially predicting the most likely next word, or token as they call it, in the sequence.
Right.
Your prompt acts as a very specific guide, influencing which tokens the model's going to choose next.
Right. So prompt engineering isn't just about luck then. It's about intentionally designing high-quality prompts to get the accurate outputs we're actually looking for.
Exactly.
The paper makes it pretty clear it's not just like asking a question and hoping for the best.
No, definitely not.
It's an iterative process, a bit of back and forth sometimes.
Yeah.
Right? To fine-tune your prompts.
Trial and error.
That involves thinking about the length, the language you use, the overall structure, all in relation to what you're trying to achieve.
And what's fascinating here, looking at the source paper, is the sheer range of things you can accomplish with well-crafted prompts.
Yeah, like what?
Well, everything from summarizing really lengthy documents to pinpointing specific bits of information, answering questions directly, categorizing different types of text, translating languages, and that even includes programming languages.
Wow.
Generating new code, and even using these models to understand and explain existing code. It's a truly versatile set of tools at your fingertips if you know how to prompt them.
And it's important to remember, too, that the specific large language model you're using can make a difference. The paper points this out.
Oh, for sure.
Whether you're using Gemini through Vertex AI or maybe something like GPT, Claude, or even, open source options like Gemma.
Yeah, lots of choices now.
You might need to adapt your prompt slightly to get the optimal performance from each one. They're not all identical.
Absolutely. But it's not just about the prompt itself. The paper makes a really crucial point about how you configure the LLM's output.
Okay. So beyond the words we type in.
Exactly. There are some really important settings you can control beyond just the text you provide as input.
Okay, let's talk about those output controls then. The paper starts with output length. What's that about?
Yeah, output length basically refers to the maximum number of tokens the LLM will generate in its response.
Tokens, so words or parts of words.
Right. And it's tempting to think, asking for a longer output will automatically give you a more thorough or even a more concise answer somehow.
Yeah, I could see that.
But the paper clarifies that simply increasing the token limit just makes the output longer. It doesn't guarantee conciseness. It's more about setting an upper boundary.
Okay.
However, as we'll see maybe later with some more advanced techniques like React, having a longer output window can actually be important for the model to show its reasoning steps.
Oh. Okay, that makes sense. So longer isn't necessarily better for just getting a succinct answer.
Not always, no.
Now, tell me about these sampling controls. That sounds like where we can really influence the AI's response style, maybe.
Exactly. This is where you start to influence how creative or predictable the LLM's responses are going to be.
Okay.
The paper highlights 3 key settings here: temperature, top K, and top P.
Right.
Let's start with temperature. Think of this as controlling the randomness in the model's token selection process.
Randomness. Okay.
Yeah. So a lower temperature makes the LLM more focused and predictable. It's more likely to choose the most obvious next word, leading to more consistent, maybe factual results. A temperature of 0, which they actually call greedy decoding, means the model always picks the single most probable token. no variation.
So if you want a straightforward, almost definitive answer, you'd crank the temperature down low.
Precisely, yeah, go low for that. On the other hand, a higher temperature injects more randomness.
Okay.
The model will consider a wider range of less likely tokens, which can lead to more surprising, diverse, and, well, creative outputs. The paper even uses the analogy of the softmax function in machine learning. Imagine it like a probability distribution over all possible next words.
Right.
A higher temperature makes that distribution flatter, basically giving more words a chance of being selected.
So it spreads the odds out a bit more.
Exactly. They suggest that for coherent results that still have some creative flair, maybe starting around a temperature of 0.2 might be good.
Okay. A little bit of creativity.
If you're really aiming for creative and unexpected responses, you could try something higher, like maybe 0.9.
Wow. Okay.
And if you need very focused, less creative results, perhaps around 0.1. And for tasks with like a single correct answer, a calculation or something, they recommend starting with a temperature of 0.
Got it. So temperature is like a knob you can turn to make the AI more or less adventurous in its word choices.
Pretty much, yeah. That's a good way to put it.
What about top K and top P then? How do they fit in?
Right, so these are two other methods for influencing the randomness and diversity, basically by narrowing down the pool of potential next tokens the model considers.
Okay. Narrowing it down.
Yeah. Top K sampling looks at the top K, most likely tokens, predicted by the model, and only selects from that specific set.
So K is a number, like the top 5.
Exactly. A higher K means more options are considered, leading to more varied output, while a lower K makes the output more focused and factual. A top K of 1 is essentially the same as that greedy decoding we talked about, 0 temperature.
Okay, so K is like saying, out of all the words the AI thinks could come next,
Yeah.
only consider the top, say, 10 of them.
Exactly right. Now, top P, sometimes called nucleus sampling, works a little differently.
Okay.
Instead of a fixed number like K, it looks at the cumulative probability of the predicted tokens. It selects the smallest set of tokens whose total probability adds up to exceed a certain threshold, P.
Okay, probability-based.
Yeah, so if you set P to 0.9, it will consider the top tokens that together make up 90% of the probability distribution. Similar to top K, a lower P makes the output more predictable, while a higher P allows for more diversity. The paper suggests experimenting with both top K and top P, maybe on their own, maybe together, to see what works best for the specific kind of output you're aiming for.
And how do these all interact? It sounds like you could have temperature, top K, and top P all set at the same time.
That's right, you can. And it's important to understand how they work together. If all three are enabled, the model first identifies the tokens that satisfy both the top K and top P criteria.
Okay, the intersection.
Then the temperature setting is applied to randomly select from just that smaller set of candidate tokens.
Right.
If only top K or top P is active, then only that filter is used. If temperature isn't specified, the model will just randomly choose from the tokens that pass the top K and or top P filter.
Makes sense.
The paper also notes that at very extreme settings, one control can essentially dominate the others. Like if you set the temperature to 0, top K and top P basically become irrelevant because the model will always just pick the single most likely next token.
Okay, similarly, a top K of 1 also overrides the others. Same effect.
That's good to know you can sort of simplify things if you have a very specific kind of output in mind. Now, the paper also mentions something called the repetition loop bug. That doesn't sound good at all.
No, it's not ideal. It's a fairly common issue with LLMs where they can get stuck in a loop, just repeating the same word or phrase or sentence structure over and over again, like a broken record.
Yeah, I think I've seen that happen. Why does it occur?
Well, the paper explains that this can actually happen at both very low and very high temperature settings. Interestingly enough, though, for different reasons.
Oh.
At low temperatures, the model can become too predictable and just keep following a path that, well, leads back to previously generated text.
Okay.
At high temperatures, the increased randomness can, just by chance, sometimes lead it back to a prior state as well.
And inappropriate top K and top P settings can also make this worse. The solution usually involves carefully adjusting these sampling controls, temperature, top K, top P, to find the right balance between predictability and randomness for your task.
Okay, so it's about finding that sweet spot in the output configuration to get the kind of response you want without the AI getting stuck.
Exactly, fine-tuning those knobs.
Now let's move on to what I think is maybe the most interesting part, the actual techniques for crafting effective prompts. The paper covers quite a few. Let's kick things off with general prompting or zero-shot prompting.
Right, zero-shot prompting is probably the most straightforward approach. You essentially just give the LLM a description of the task and maybe some initial text, but critically, without providing any examples of the desired output.
Okay, 0 examples.
Yeah, the zero-shot part means you're giving the model 0 examples to learn from for that specific query. The paper gives a good illustration of this with a movie review classification task. The prompt was something like, classify movie reviews as positive, neutral, or negative. Review. Her is a disturbing study revealing the direction humanity is headed if AI is allowed to keep evolving unchecked. I wish there were more movies like this masterpiece. Sentiment.
And what happened?
They used the Gemini Pro model, set a low temperature of Blate 1, and the output was simply positive.
Wow, just like that?
Just like that. It's quite impressive that even without specific examples, the model can often understand the task and provide a relevant sentiment or answer.
It is interesting. But the paper also points out that, sometimes 0 shot isn't quite enough, and that's when we move on to 1 shot and few shot prompting.
Exactly. This is where you start including examples within your prompt to guide the model more explicitly.
Okay.
A 1-shot prompt has just a single example, while a few-shot prompt provides multiple examples. The paper suggests maybe around 3 to 5 is often a good starting point.
And why use examples?
These examples are particularly useful when you want to steer the model towards a specific output structure or format or even a particular style.
Ah, right.
The idea is that the model can learn from these examples you provide and then mimic them to better complete the task you've set. Show, don't just tell.
The paper has that example of taking pizza orders in plain language and parsing them into a JSON format using a few-shot prompt.
Yeah.
Can you walk us through that?
Certainly. So the goal was to take natural-sounding pizza orders, like someone just talking,
Yeah.
and convert them into a structured JSON format, which is useful for computers.
Mm-hmm.
So they provided 2 examples in the prompt itself. The first was an order like, I want a small pizza with cheese, tomato sauce, and pepperoni, followed by the desired JSON output showing those details structured.
Okay, 1 example down.
The second example was a larger, maybe more complex order with different toppings and its corresponding JSON structure. Then, after those 2 examples, they gave the actual prompt. Now, I would like a large pizza with the first half cheese and mozzarella, and the other tomato sauce, ham, and pineapple.
And the model.
Because the model had seen the pattern in the 2 examples, how to structure the toppings, sizes, halves, it was able to correctly output the JSON representing that new half-and-half pizza with the specified toppings.
That's pretty powerful. It's like teaching the model by showing it exactly what you want the output to look like.
It is. It learns the format and the logic from the examples.
The paper emphasizes that the quality of these examples is really important, right? Like super important.
Absolutely crucial. The examples should be directly relevant to the task, obviously. They should represent the kind of variety you expect in the inputs and outputs.
Okay.
They need to be well-written and critically accurate. Even a small mistake in an example can seriously confuse the model and lead to less desirable results.
Garbage in, garbage out, basically.
Pretty much. And if you want your model to be able to handle a wide range of inputs, including those that might be a bit unusual or unexpected,
Yeah.
the paper recommends including edge cases in your examples, those less common scenarios that you still want the model to handle correctly. Think about the weird orders.
Good tip. Cover your bases. Okay, so examples are key for showing the model the desired output and how to handle different situations. Now, the paper also talks about system, contextual, and role prompting. These sound like different ways to frame the instructions we give to the AI.
They are indeed, and while there can be some overlap between them sometimes, each focuses on a slightly different aspect of guiding the LLM.
Okay, break them down for us.
So system prompting is about setting the overall context and the overarching goal for the model, kind of the big picture of what it should be doing.
Like the main job description.
Yeah, exactly. Like translate this text into Spanish or classify this customer feedback as positive or negative. That's a system prompt.
Got it. Contextual.
Contextual prompting provides specific details or background information that's relevant to the immediate conversation or task. This helps the model understand the specific nuances of what's being asked right now.
Okay, adds more detail. And role prompting.
Role prompting involves telling the model to adopt a particular persona or identity.
Ah, like act as a...
Precisely. Act as a pirate. Act as a helpful assistant. This helps it generate responses that are consistent with the knowledge, behavior, and communication style of that specific role.
Can you give us a practical example of system prompting in action based on the paper?
Certainly. The paper shows an example where the main goal is still to classify movie reviews, like before,
Yeah.
but the system prompt adds a very specific instruction. Only return the label in uppercase.
Controlling the format.
Exactly. And by also setting a higher temperature, in this instance, they used 1.0, they allowed for maybe more creative language in the reasoning part, which wasn't explicitly asked for in the output. But because of that clear system instruction about the output format, the model still correctly classified the review as negative, but crucially in all capital letters.
Neat.
Another really powerful application of system prompting they highlight is explicitly defining the desired output format, like requesting the output in JSON.
We touched on that with the pizza example.
Yeah, exactly.
Yeah.
They provide an example of classifying a movie review and clearly outlining the JSON schema for the output, specifying the fields, sentiment, reasoning, and their expected data types, string.
Okay.
This not only structures the data in a useful way, which is great for applications, but it also helps to reduce the likelihood of the model just making stuff up, hallucinating irrelevant information, because it has a predefined format to stick to.
That JSON output example looked really useful for getting structured data back. What about role prompting? How does that work in practice?
So with role prompting, you essentially tell the model to act as if it were a specific type of person or entity. The paper has a really illustrative example where they prompt the model. I want you to act as a travel guide. I will write to you about my location, and you will suggest 3 places to visit near me. In some cases, I will also give you the type of places I will visit.
Right.
My suggestion. I am in Amsterdam, and I want to visit only museums. Travel suggestions.
And what did it do?
The model, taking on that role of a travel guide, then provides 3 relevant museum suggestions in Amsterdam, just like asked.
Cool.
And the paper also emphasizes how changing the role, like asking it to act as a history professor instead, would likely yield a very different kind of response, perhaps with more historical context for the museums, not just tourist info.
Makes sense. The role dictates the style and knowledge.
Exactly. They even experimented with adding a specific style to the role, like asking the travel guide to be humorous.
Oh, fun.
Yeah. And that resulted in much more entertaining and personality-driven suggestions for visiting Manhattan.
That's a fun way to get more tailored and engaging responses. And contextual prompting, how does providing that specific context help the model?
Right. Contextual prompting is all about giving the LLM specific background info that's directly relevant to the task at hand.
Okay.
The paper demonstrates this with an example where the goal is to suggest article topics for a blog, but not just any blog, a blog focused specifically on retro 80s arcade video games.
Meech.
Very. So the prompt begins by setting that context. You are writing for a blog about retro 80s arcade video games.
Establishes the domain.
Exactly. Then it directly asks for 3 article topic suggestions, along with a brief description for each.
And because it knew the context.
The suggested topics were highly relevant, like the evolution of arcade cabinet design or blast from the past, iconic arcade games of the 80s, much better than just general video game ideas.
Right. Without that initial context, the suggestions might have been way too broad or just completely off topic for that specific blog.
Precisely. That context acts like a filter.
So providing that specific context helps the model narrow its focus and generate ideas that are much more targeted and useful. Okay, now the paper moves on to some more advanced techniques. Step-back prompting sounds really interesting. What's that?
Step-back prompting is a really clever technique, actually. It's designed to enhance the model's reasoning capabilities, especially for complex stuff.
Okay. Wow.
The fundamental idea is that before you ask the LLM to perform a specific complex task, you first prompt it with a more general but related question.
Warm-up question.
Kind of, yeah. This initial step back allows the model to activate relevant background knowledge and engage in broader reasoning about the topic. Then you take the answer it provides to that general question, and you incorporate that into a subsequent prompt for the original, more specific task.
Huh. Can you give us a clear example of how this step-back approach works?
Certainly. The paper uses the example of wanting to write a storyline for a level in a first-person shooter video game.
Okay, game design.
Yeah. A traditional prompt might just ask for, a challenging and engaging storyline.
Pretty generic.
Right. But with step-back prompting, they first ask something like, based on popular first-person shooter action games, What are 5 fictional key settings that contribute to a challenging and engaging level storyline?
Asking about common tropes or settings first.
Exactly. The model might then generate a list like an abandoned military base, a futuristic cityscape, an underwater research facility, that kind of thing.
Right.
Finally, they would take one of these themes, let's say the underwater research facility, and use that as context in the final prompt to actually write the specific storyline for the level.
I see.
And the resulting storyline, because it's informed by the model's own answer to that step-back question about effective settings, tends to be much more detailed, creative, and kind of aligned with the conventions of the genre compared to what you might get from just the direct, simple prompt alone.
That's really smart. It's like priming the model's knowledge base, getting it thinking along the right lines before tackling the specifics.
Exactly. You're guiding its thought process more effectively.
Okay, next up is chain of thought, or code prompting, which I've definitely heard quite a bit about. Seems popular.
It is, and for good reason. Chain of thought prompting is a very effective technique for significantly improving the reasoning capabilities of LLMs, particularly for more complex tasks that need logic.
How does it work?
So instead of just asking the model for the final answer, you prompt it to explicitly show its reasoning process by generating a series of intermediate steps.
Like showing your work in math class.
Exactly like that. It's like asking it to think out loud. This helps the LLM arrive at more accurate conclusions, especially for problems that require logical deduction or multi-step reasoning.
And the benefits.
Well, the paper highlights that CoT is surprisingly effective even with standard. Off-the-shelf LLMs, you don't necessarily need special fine-tuning.
That's good.
It also offers a degree of interpretability, right? Because you can follow the model's thought process. That can be really useful for understanding why it arrived at a particular answer.
Or where it went wrong.
Exactly, for debugging if it makes a mistake.
Yeah.
However, there is a trade-off. Because the response includes all these reasoning steps, it naturally leads to longer outputs.
Right. More tokens.
Which can have implications for cost and processing time, depending on the model and platform.
The paper has that great example of a simple math word problem, where the initial answer is wrong, but then using CoT helps the model get it right. Can you explain that one?
Yeah, it's a good illustration. The initial prompt was a seemingly straightforward word problem. When I was 3 years old, my partner was 3 times my age. Now I am 20 years old. How old is my partner?
Okay, sounds simple enough.
But the model's initial answer without CoT was actually incorrect. It said 63.
Whoa, way off.
Right. But when they simply added the instruction, let's think step by step, prompting the model to show its reasoning, it correctly broke down the problem. First, it calculated the partner's age when the person was 3, which is 9. Then it found the age difference, 6 years. Then it applied that difference to the current age, 20 plus 6, to arrive at the correct answer of 26.
The step-by-step logic fixed it.
Exactly. They also illustrate how you can further enhance this with what they call a single-shot COT example.
Okay.
This involves providing one correct example of step-by-step reasoning in the prompt itself right before you pose the target question. This gives the model an even clearer template to follow for its own reasoning process.
So showing it how to show its work.
Precisely.
So by explicitly asking the model to explain its thinking, we can dramatically improve its ability to solve problems that require more than just, like, recalling information.
Definitely seems to help with reasoning tasks.
The paper also discusses self-consistency. How does that build upon this idea of chain of thought?
Right. Self-consistency tries to address a potential limitation of basic COT. COT often relies on a relatively straightforward, maybe greedy approach to generating the reasoning steps, sometimes just picking the single most probable next step at each point.
Okay.
Self-consistency takes this further by combining sampling with a kind of majority voting approach.
How does that work?
You essentially prompt the LLM multiple times with the same question, but, and this is key, you use a higher temperature setting.
More randomness.
Exactly. To encourage it to explore a diverse range of different reasoning paths each time it answers.
Okay, so you get multiple different attempts at reasoning.
Yes. Then you extract the final answer from each of these generated responses, and you choose the answer that appears most frequently across all the attempts. That's your final self-consistent result.
Safety in numbers, sorta.
Kind of, yeah. It can significantly improve the accuracy and reliability of the answers, especially for tasks where there might be multiple valid ways to arrive at the solution. But again, it does come with a higher computational cost since you're generating multiple reasoning paths for the same question.
Makes sense. More work, potentially better answer.
The paper uses an email classification example. Initial zero-shot COT attempts might yield slightly different classifications for a tricky email.
Hmm.
By using self-consistency, generating several reasoning paths, and looking at the most common classification across those attempts, you'd be much more likely to nail down the most accurate categorization.
That makes sense. It's like getting multiple opinions from the same expert
Yeah.
who might think slightly differently each time, and then going with the consensus.
A good way to think about it, yeah.
The paper also briefly mentions tree of thoughts, or TOT, as another advanced technique. What's the gist there?
Yes, TOT is presented as basically a more generalized version of chain of thought.
Okay.
Instead of following just a single chain of reasoning, it allows the LLM to explore multiple different reasoning paths in parallel, kind of organizing them in a tree-like structure.
Branching paths.
Exactly. This is particularly useful for tackling very complex tasks that might require exploring various options, evaluating different approaches, and maybe even backtracking if a particular path doesn't seem promising. It offers even more flexibility in the reasoning process compared to just a linear chain of thought.
Sounds powerful, but probably complex to set up.
Likely, yes. It's more advanced.
And then there's REACT, which stands for Reason and Act. That sounds like it goes beyond just generating text.
It really does. REACT is a more sophisticated paradigm, you could say, that enables LLMs to solve complex, knowledge-intensive tasks by combining their natural language reasoning with the ability to interact with external tools.
Tools, like what?
Like search engines, databases, knowledge bases, maybe even code interpreters, things outside the model itself.
Wow. How does that work?
It's inspired by how humans often approach problem solving, right? We reason about what information we need. Then we take actions like searching the internet or looking something up to gather that information.
Right.
And then we use that new information to continue reasoning and maybe take further actions until we find a solution. REACT tries to mimic this loop.
Okay, so it thinks, acts, observes, thinks again.
That's basically the loop. Thought, action, observation, thought. The paper provides a really compelling Python LangChain example. They use REACT with a search tool to figure out the total number of children of all the members of the band Metallica.
Okay, that's not something the base model would just know.
Exactly. So the model goes through a cycle. Thought. I need to find the number of children for each band member. Action. Use the search tool to look up children of James Hetfield. Observation. Get the search result. Thought. Okay, he has X children. Now I need Lars Ulrich. Action. Search for Lars. And so on.
I see. It actively gathers the data it needs.
Yes. It observes the results from the tool and uses that information to continue reasoning, maybe summing up the numbers, until it arrives at the final answer.
That's incredible.
It is. This approach requires more intricate setup, definitely. You need to define the tools the LLM can use and manage the back and forth of prompts and responses. But it significantly expands the capabilities of LLMs by allowing them to access and incorporate information way beyond their initial training data.
That's truly fascinating. The AI can actively go out and retrieve information to inform its reasoning. Now, what about taking some of the work out of prompt engineering itself? The paper touches on automatic prompt engineering, or APE. Sounds appealing.
It is a really intriguing area, yeah. APE aims to automate the often tedious, iterative process of discovering effective prompts.
Wow.
The core idea is basically to use a language model itself to generate a diverse set of potential prompts for a specific task.
Meta.
Totally. Then you automatically evaluate the performance of these generated prompts based on some predefined criteria, and finally, you select the prompt that yields the best results according to those criteria.
You give an example.
The paper provides an example of trying to find different and effective ways a customer might order a band t-shirt through a web shop chatbot.
What?
They'd prompt another model, an instructor model, to generate, say, 10 different phrasings for this request. I want a Metallica shirt, show me size large band tees, etc. Then they suggest evaluating these generated prompts using metrics like BLA-EU or RU score. These are common in NLP for assessing the quality of generated text by comparing it to human-written reference examples.
Okay, so you score the generated prompts.
Exactly. The prompt that receives the highest evaluation score is then considered the best one found so far, and you can use that in your actual chatbot.
Cool.
You can even take the top performing prompts and feed them back into the process to further refine them, repeating the generation and evaluation cycle to potentially discover even better prompts over time. It's like using AI to help us become better at instructing AI.
So it's like a meta-level optimization where AI helps us fine-tune how we interact with AI. That's a really interesting direction. The paper also has a dedicated section on code prompting. How can we specifically leverage LLMs for tasks related to software code?
Yeah, Gemini, along with other advanced LLMs, has shown a really strong aptitude for working with code. It's becoming incredibly helpful for a wide range of coding-related tasks. While writing new code from scratch, obviously, but also providing clear explanations of existing, maybe complex code, translating code between different programming languages, what's a big one,
Oh, wow, yeah.
and even assisting with the often challenging processes of debugging and reviewing code to identify errors and suggest potential improvements.
So a real coder's assistant.
Pretty much. The paper provides several practical examples using both Bash scripting and Python.
Okay.
For instance, they show a prompt asking Gemini to write a Bash script that will rename all files in a given folder by adding the prefix draft to each file name.
Useful utility.
And the generated code is not only functional, but also includes helpful comments explaining what each part of the script does, which is nice.
Very helpful.
They further demonstrate how you can then take that same Bash code and ask the model to provide a detailed explanation of its functionality or translate it into Python code.
Okay.
And they even show presenting the model with a Python script that contains an error along with its traceback message
The error message, yeah.
and asking the model to identify the bug and suggest a corrected version. In all these cases, the model demonstrates a strong understanding of programming concepts and the ability to generate and reason about code pretty effectively.
These code examples are really compelling. It really sounds like LLMs can be an invaluable tool for developers at various stages of the software development lifecycle.
I think so, yeah. It's changing how people code.
And the paper also briefly mentions multimodal prompting. Just a quick touch on that.
Yeah, the paper touches on this mainly to acknowledge that while their primary focus has been on text-based prompts, the field is rapidly advancing toward using multiple input formats beyond just text.
Like images, audio.
Exactly. Multimodal prompting involves using combinations of text, images, audio, code, maybe video, other types of data as input to guide large language models that have the architectural capability to process such diverse information.
So the prompt isn't just words anymore.
Potentially, no. This opens up a whole new realm of possibilities for how we can interact with and instruct these powerful AI systems in the future. It's a big area of research.
Okay, wow. We've covered a huge amount of ground with all these different prompting techniques. Now let's maybe shift gears and move on to the crucial best practices that the paper outlines for really becoming proficient at prompt engineering.
Absolutely. This is where the rubber meets the road, really. The first and perhaps most fundamental best practice they mention is to provide examples in your prompts whenever possible. Use that one-shot or few-shot prompting we talked about.
Right, the showing versus telling idea.
Exactly. As we've discussed, this serves as an incredibly effective way to teach the model the specific output format, style, tone, whatever it is you're looking for. Think of it as showing rather than just telling.
That makes perfect sense. Actions speak louder than words, even with AI instructions, it seems. What's the next key best practice?
The paper strongly emphasizes the importance of designing your prompts with simplicity in mind.
Keep it simple.
Yeah. Your prompts should be as concise, clear, and straightforward as possible. Make them easy for both you and the model to understand. Avoid using overly complex language, jargon if you can help it, or any unnecessary information that could potentially confuse the model.
Good advice.
They even provide a neat before and after example of a prompt for a travel guide, illustrating how making it more direct and using strong action verbs like act and describe can significantly improve its effectiveness.
Simplicity is key. Don't try to overcomplicate your instructions. What about how specific we should be then? Is simple too vague sometimes?
Good question. The next practice is be as specific as possible about the desired output.
Okay, so balance simplicity with specificity.
Exactly. A vague or general instruction might not give the LLM enough direction to produce the kind of result you're actually hoping for.
Right.
Provide sufficient detail in your prompt. You can use system or contextual prompting to help set the stage, to help the model really understand what you need. This improves the accuracy and relevance of its response.
Can you give an example of that contrast?
Sure, they contrast a very general prompt like, tell me about video game consoles, with a much more specific one that asks for, say, a 3-paragraph blog post written in a conversational style, focusing on the top 5 consoles, listing their manufacturers, release years, and maybe sales figures.
Much clearer goal.
Right. The more specific prompt is far more likely to yield a useful, targeted result than the super vague one.
So the more detail you provide about your expectations, the better the model can meet them. The next best practice is interesting. Use instructions over constraints. Can you elaborate on that one?
Yeah, this is a subtle but important point. The paper highlights that it's often more effective to focus on giving the model positive instructions telling it what to do rather than primarily relying on constraints telling it what not to do.
Why is that?
Well, it kind of aligns with how humans generally respond better to positive guidance, right? Clear instructions directly communicate the desired outcome, whereas a long list of don'ts might leave the model unsure of what is actually allowed or desired.
Mhm.
Constraints still have their place, of course, especially when it comes to safety or enforcing really strict output formats. But the general recommendation is to prioritize positive instructions whenever you can.
Got it.
They provide another example related to that blog post about video game consoles, showing how you can achieve a specific focus and tone by instructing the model on what key elements to include, rather than just listing things to avoid.
That's a valuable shift in perspective. Focus on the positive outcomes you want rather than just trying to prevent the undesirable ones. What about managing the length of the AI's response? We talked about output tokens earlier.
Right. You can, and often should, control the maximum token length of the LLM's output.
How?
This can be done either through the configuration settings of the LLM you're using. Most platforms have a slider or box for max tokens, or sometimes by explicitly stating your desired length in the prompt itself.
Oh, like asking for a summary in 100 words.
Exactly, or like their example, asking for an explanation of quantum physics in the length of a tweet. This helps manage resources, prevents overly long responses, and ensures the output is appropriately sized for your needs.
Makes sense. Be mindful of how much text you're asking the AI to generate. The paper also mentions the benefit of using variables within your prompts. How can that be useful?
Right. Using variables in your prompts can make them much more flexible, reusable, and dynamic. It's really handy.
How does that work?
Instead of directly embedding specific pieces of information like a city name into the prompt every time,
Yeah.
you can use placeholders, often like curly braces, city name, or something similar. Then you can easily change or fill in those placeholders with different values depending on your specific needs at that moment.
Ah, like a template.
Exactly. The paper provides a simple example of asking for a fact about a city, using city as a variable that can then be set to Amsterdam, Tokyo, or any other city you're interested in, without rewriting the whole prompt.
I can see how that would be super useful for applications.
Yeah, it's particularly useful when you're integrating prompts into applications or workflows where you'll be processing multiple different inputs using the same basic prompt structure.
That's a great way to make your prompts more adaptable. What about trying out different ways of phrasing things? Does wording matter that much?
It definitely can. The advice is to experiment with different input formats and writing styles for your prompts.
Okay.
You might actually be surprised by how even slight variations in your prompt's wording or its structure, or even whether you phrase it as a question versus a statement versus a direct instruction, can lead to different and sometimes better results.
Really?
Yeah. The paper gives an example of generating text about the Sega Dreamcast using these 3 different input styles: question, statement, instruction, and notes, that they can indeed yield different outputs. Some might be more aligned with your goal than others.
Interesting. So don't be afraid to try different angles and phrasings to see what works best for a particular task.
Exactly. Iterate on the phrasing itself.
For those using few-shot prompting for classification tasks, the paper has a specific recommendation about the examples.
Yes, this is important for few-shot classification. Mix up the classes within your examples.
What does that mean?
If all the examples for, say, positive reviews appear together, followed by all the examples for negative reviews,
Yeah.
the model might incorrectly learn to associate the category with the order of the examples rather than the actual features of the text in each class. It picks up a false pattern.
Ah, I see. That could lead to errors.
Right. Mixing the examples from different classes helps the model learn the underlying distinctions more effectively, leading to more robust performance on new, unseen data. They suggest starting with around 6 examples maybe, and ensuring a good mix of the different categories within those examples.
That's a really helpful practical tip to avoid unintentionally biasing the model. Good one. What about keeping up with the ever-evolving landscape of these AI models? They seem to change constantly.
That's another best practice. Adapt to model updates. You really have to.
It's moving fast.
Incredibly fast. The field of large language models is constantly advancing. New models are being released with improved architectures, larger training data sets, enhanced capabilities. It's nonstop.
So what should we do?
It's important to try out these newer versions of models as they become available and be prepared to adjust your existing prompts. Sometimes prompts that worked great on an older model might need tweaking, or newer models might enable entirely new prompting approaches.
Where can we do that easily?
Platforms like Vertex AI Studio are often invaluable for this. They let you keep track of different models and versions and easily test how your prompts perform across them.
Staying current is definitely key in this rapidly developing field. The paper also emphasizes experimenting with different output formats again.
Absolutely. Experiment with different output formats, particularly for non-creative tasks like data extraction or categorization or summarization.
Like JSON.
Exactly. The paper strongly recommends using structured formats like JSON or maybe XML whenever it makes sense for your application. They really reiterate the numerous benefits of using JSON.
Remind us what those are.
Sure. Things like ensuring consistent styling, keeping the focus squarely on the data itself, reducing the likelihood of the model hallucinating extraneous information, explicitly defining relationships between different pieces of data, the ability to specify data types, like number versus string, and just the general ease of sorting and processing the output programmatically.
Right.
They refer back to their earlier example of classifying movie reviews and outputting the result in JSON format as a prime illustration of these advantages. Much easier to work with than just plain text.
Structured output like JSON sounds incredibly useful.
Yeah.
Especially for integrating LLM results into other systems and for reliable data handling downstream.
Definitely. If you need data, ask for structured data.
The paper also briefly mentioned something called JSON repair. What's the context there? Sounds useful.
It can be. Because JSON, with its brackets and quotes and commas, can be more verbose than plain text.
Yeah, takes up more tokens?
Right. It's sometimes possible that you'll hit the output token limit in the middle of the model generating a JSON object.
Ah, so you get cut off. Incomplete JSON.
Exactly, resulting in a truncated and therefore invalid JSON structure. JSON repair tools, like the JSON repair library they mentioned for Python, are designed to automatically attempt to fix these incomplete or malformed JSON outputs. They try to intelligently close brackets, add missing commas, etc.
So it can salvage the response.
Potentially, yeah. It can make them usable even if they were cut off prematurely. This can save you from having to discard the entire response and rerun the prompt, which saves time and maybe money.
That's a very practical tip for anyone working with JSON output from LLMs. Good to know about. And what about the idea of working with schemas? How does that relate?
Right. So while we've discussed using JSON for structuring the output from the LLM, the paper also highlights the significant benefits of working with schemas to define the expected structure and data types of the input you provide to the model, especially when you're sending structured data in your prompt.
Defining the input structure too.
Exactly. A JSON schema acts like a blueprint, clearly outlining what kind of data the model should expect in the input.
Why is that helpful?
By providing a schema along with your data, you give the LLM a much clearer understanding of what information is important and how it's organized. This can help it focus on the relevant parts of the input and reduce the chances of it misinterpreting what you've sent it.
Makes sense. Clarity for the model.
Schemas can also be used to establish relationships between different data points within your input, and even to specify formats for things like dates and times, making the input more precise and easier for the model to understand correctly.
Do they have an example?
Yeah, they provide an example of using a schema to define the attributes of a product in an e-commerce catalog, like name, description, price, features. Then you provide the actual product data as a JSON object that adheres to this schema. This kind of structured input can lead to much more accurate and relevant product descriptions generated by the LLM because it knows exactly what input fields it's working with.
So, schemas can provide valuable structure and clarity for both the input and the output, leading to more reliable interactions with the AI.
That's the idea, yes. More predictable interactions.
The paper also suggests a collaborative approach to prompt engineering. Tell us about that.
Yeah, they recommend experimenting together with other prompt engineers whenever possible. It can be incredibly beneficial.
Why? Two heads better than one.
Pretty much. When you're trying to figure out the most effective way to prompt for a specific, maybe tricky task, getting input and seeing different approaches from multiple people can often lead to breakthroughs you might not have found on your own. You'll likely see a range of performance across different attempts from different people, and you can learn valuable lessons from each other's successes and, just as importantly, failures.
A collaborative environment can definitely foster innovation and lead to better solutions faster. Good point. The paper also has some specific best practices just for chain of thought prompting.
Yes, a few key ones for COPT. First, they emphasize the importance of placing the final answer after the reasoning steps in the output.
Why does the order matter?
Apparently, the process of the model generating the intermediate reasoning actually influences the tokens it considers when it's predicting that final answer. So reason first, then answer.
Okay.
Also, for both COPT and self-consistency, you need to make sure you can clearly extract the final answer from the full response. You need a reliable way to separate it from all the preceding reasoning steps, especially if you're automating this.
Right, for programmatic use.
And finally, for COPT prompting specifically, they often recommend setting the temperature to 0 or a very low value.
Why low temp for COPT?
Because reasoning tasks typically have a single correct logical path or answer, and COPT relies on a more deterministic step-by-step approach to its reasoning process. High randomness isn't usually helpful when you want logical deduction.
Those are important nuances for getting the most out of chain of thought prompting.
Yeah.
Makes sense. And the final best practice the paper highlights seems crucial. It's all about documentation.
Absolutely crucial. They really stress this. Document your various prompt attempts in thorough detail, like really document them.
What kind of details?
For each attempt, keep track of the specific goal you were trying to achieve, the exact model you used, including its version if applicable, all the configuration settings, temperature, token limits, top K, top P.
Okay, the whole setup.
The complete text of your prompt, naturally, the full output you received from the model, and importantly, a clear indication of whether the result was satisfactory, okay or not okay, and maybe some feedback notes on why.
Wow, that's detailed.
It is. If you're using a platform like Vertex AI Studio, make sure to save your prompts there and maybe link to them in your documentation spreadsheet or wherever you're tracking.
Okay.
For more complex systems that might involve retrieval augmented generation or RAD,
Yeah.
document the specifics of your RE setup as well, what documents were retrieved, etc. And once you've identified prompts that work well, it's really best practice to save them in your actual code base.
To store them with the code.
Yeah, ideally in files separate from your main application code so they're easy to manage. And even better, set up automated tests to ensure they continue to perform as expected whenever you make changes to your system, or, importantly, when the underlying AI models are updated.
Proactive testing.
Exactly. The paper even provides a helpful template for a Google Sheet that you can use to systematically track all of this information. It's really about being methodical.
Thorough documentation really does seem essential for learning, iterating effectively, and just maintaining your prompt engineering work over time. Seems non-negotiable for serious work.
It really is if you want repeatable, reliable results.
And the paper concludes by reminding us that prompt engineering is indeed, as we said, an iterative process, right?
Exactly. You craft your prompt, you test it out, you carefully analyze the results, you document everything meticulously, and then you refine your approach based on what you've learned. It's a cycle.
Craft, test, analyze, document, refine, repeat.
That's the loop. And don't be afraid to keep experimenting. And whenever the underlying models change or your configuration settings change, it's always a good idea to revisit your previously successful prompts to see how they perform now and if any adjustments are needed.
Well, this has been an incredibly insightful deep dive into the world of prompt engineering. Seriously useful stuff.
Glad it was helpful.
We've explored the foundational principles of how LLMs work and how to configure their output. A really impressive range of powerful prompting techniques with concrete real-world examples.
Yeah, lots of techniques out there.
And a comprehensive set of best practices that can truly help anyone listening elevate their ability to get the most out of these amazing tools.
And what's truly remarkable, I think, is that by grasping these concepts and techniques, you, our listener, now have a significant advantage. A real shortcut, maybe to effectively harness the immense power of these language models.
Yeah.
Whether it's to tackle your specific professional challenges, or maybe just to satisfy your own curiosity and gain knowledge quickly and thoroughly in whatever area interests you.
So here's maybe a final thought to really consider. Now that you have a much deeper understanding of how to guide these incredibly powerful language models with greater precision and intention, what exciting new possibilities for learning, creating, and problem-solving will you now explore?
Good question.
Think about the information sources you rely on. Maybe the questions you've always had. How might you apply these techniques, maybe CoT or React, or even just better few-shot prompting, to unlock even deeper insights and find more effective solutions?
Yeah, we strongly encourage you to delve further into the specific prompting techniques that sparked your interest during this dive, and maybe share your own experiences and experiments as you start applying these ideas.
Definitely.
This is truly just the beginning of a fascinating and constantly evolving journey into the world of interacting with artificial intelligence. There's always more to learn.